Hello, this is a short unit that's preliminary to convolutional neural networks, which we'll take up in more detail in the next unit. Here we're going to do Einstein notation. Einstein notation is going to provide a sort of simpler and clearer notation, and it will be particularly effective in convolutional neural networks. And it's a notation that we'll use throughout the rest of this class. So let's get started. So Einstein notation was developed by Einstein as part of the notation for general relativity. And the basic idea is that we leave all the indices explicit. And in general relativity and in deep learning, we're dealing with tensors with many indices, 4, maybe 5 indices. And the notation can get very confusing if we try to use matrix notation. But the notation that suppresses the indices, like vector matrix products, is a kind of notation that's used more in the frameworks. So we're going to trade conceptual clarity for the class, for understanding algorithms and ideas, for simple translation into framework code. There always is a translation into framework code, but we're going to focus on achieving the conceptual simplicity of Einstein notation. Okay. Let's start. We're going to start by just considering matrices and vectors. Now, Einstein notation doesn't really improve the clarity of simple matrices and vectors. So we're just doing this to introduce the notation, to make the notation clear. And the notation will sort of show its power when we get to convolution, which we'll do at the end of this unit. So what we're going to do is we're going to introduce this. It's really a modified Einstein notation based on using capital letters to indicate slices of tensors. So a capital letter is going to represent a slice. So let's go just do this by example. So if I have a matrix M and I write Mij, these are lowercase, then this expression denotes a particular entry in this matrix. This expression now denotes a scalar value for that matrix. If I write Mi capital J, this is a kind of slice. This is going to denote the ith row of the matrix M. Similarly, if I denote M capital I little j, that's going to be the jth column of M. And if I use 2 capital letters, that's going to denote the full matrix. Now, where Einstein notation really has its power, creates its simplicity, is in summations. So again, we're just dealing with matrices and vectors just to introduce the notation, just to get familiar with the notation. Its real clarity will show up later. So I can write y equals the matrix W, some weight matrix, times a vector x. So this is standard matrix notation. Now, if we write that out in a summation, what this exactly means is that if I look at the ith component of y, the ith component of y is a sum over j of this product, right? You take a particular entry out of this matrix and you multiply by the corresponding entry in the vector x. So each entry in y is a weighted combination of the entries in x. And this is exactly what this means. And in Einstein notation, we suppress this summation sign and simply use a capital letter and repeat it. And we adopt the convention that a repeated capital letter is implicitly being summed over. So this isn't quite as compact as this, but it's more compact than writing out explicit summations. And similarly, we can take this expression, right? So this is x transpose multiplied by the matrix. This multiplies x by the other index in W. So that has this explicit representation. The jth component of y is the sum over I of this product. And again, this is just an explicit representation of this vector matrix product. And we can write it in Einstein notation as yj equals w equals this expression, where the I is now being implicitly summed over. So let's do convolution. So I said Einstein notation is going to show its power, its clarity, when we get to convolutional neural networks. So let's do convolutional neural networks in Einstein notation. So in order to do that, I need to introduce the layers of a convolutional neural network. each layer of a convolutional neural network is if you include the batch index, it's a fourth order or four index tensor. So this is giving you a number, a scalar, for the batch element B. This is the position in the image. The pixel in the image, or position in the image, is given by an x coordinate and a y coordinate in the image. This convolutional neural networks are applied to images. And then this index is telling you, intuitively, this is giving you the index of a particular neuron. So for a particular batch element at a particular position, we're going to have many different neurons that have produced values at that position in that batch element. And this is a kind of neuron index. Okay, so what does a convolution in a convolutional neural network do? Okay, so this is the introduction to CNNs. So basically, we're going to take some layer. This might be the input image itself. And the input image itself has 3 values at every position, RGB, 3 color values. But as you go deeper in the network, we're still going to have layers where the layers have, each layer has XY coordinates and neuron layers. And as soon as you get past the image, the number of neurons is much larger, typically hundreds or thousands or maybe 1,000. So what happens in a convolution layer of a convolutional neural network is the next layer is also this 4-dimensional fourth order tensor. And each neuron in this layer, in the next layer, is taking inputs from all the neurons in the previous layer in a spatial neighborhood. Okay, so we can think of this as a family of neurons at a particular position in the next layer, taking inputs from all the neurons in the previous layer in a neighborhood of the position of this, in the neighborhood of this position. So the way we're going to get a value for the neuron in this position is to assign weights to these inputs and then put that through a linear threshold unit. So the weights are derived from a weight matrix, and the weight matrix is, a weight tensor. The weight tensor, recall, does not have a batch index. That's just, we'll go through this in a second. There's going to be a previous layer, which is a fourth order 4-index tensor, and the next layer. And we're going to say that the value of the next layer at batch index B at position XY and neuron J is going to be the result of a particular linear threshold unit that corresponds to this neuron J. So the neuron J is going to take inputs from a neighborhood, and it's going to take inputs from all the neurons within that neighborhood. Take a linear combination of those, compare them to a threshold value, and pass that through an activation function, kind of threshold unit. So this is expressing the linear combination. So the linear combination for this output, for this particular scalar output, is going to sum over all delta x values, and that's going to give us some, you can think of that as being positive or negative, and that's going to give us some neighborhood in x. It's going to sum over the range of neighbors of y, and it's also going to sum over the neurons of the previous layer. So we're summing over the neighborhood and the neurons of the previous layer. And for each point in that neighborhood and each previous layer, this tensor is giving us a weight for the output neuron J. Okay, and so when we take that sum, these are the weights assigned to the inputs this neuron is taking for batch B, the position of that neuron X plus wherever we are in the neighborhood, the position of that neuron Y plus wherever we are in the neighborhood, and the neuron in the previous layer that we're looking on. So this is just a linear combination of all the neurons in the neighborhood at the previous layer. And then we compare that to a threshold, which is specific to this neuron. The threshold just depends on this neuron. And then this is a linear threshold unit giving this value. And I find the Einstein notation much clearer because you don't have to worry about re-representing these as matrices and index-free expressions. just one final point about Einstein notation is when you make all the indices explicit, the indices themselves tend to have types. So for example, I can have a weight matrix that depends on a time index and a neuron index. You would see this in a recursive neural network, recurrent neural network for used in language. So when you write the indices explicitly, you see the types of the indices. You also see the order of the indices. So that's going to disambiguate a matrix from its transpose. I always get confused about the order of the indices when I see a matrix used when I know that it's the same information. W and W transpose contain the same information. So I always have to remember which is which. But if you use the indices explicitly, you don't have to remember that. And in a convolutional neural network, if I have a layer and I write out all the indices, it clarifies both the type of the indices and the position of the indices in the tensor. So we're going to be using this Einstein notation throughout the class. And now we'll move on to the next unit on convolutional neural networks. Thank you.